I'm Henri from SystemX, and we prepared this presentation with Agnès, who is here too, and who can join me for the questions afterward. So we can discuss the interesting question of the assessment of AI-based system trustworthiness. How is the sound? Is it okay? Yes? Okay. So it's a very interesting question because when you think about it, every word in this title is not that easy to define and understand. Like AI, it's not that easy to compare. Is it like any software, or is it more restrictive, or what's the restriction? System, even assessment, and of course, trustworthiness. So hopefully, the presentation will make it clearer. We wanted to start with this end-to-end approach from the program Confiance.ai. So you probably saw this slide before, and there is a village about it, so feel free to have a look. You'll get more explanations. But the idea is, of course, that the trustworthiness is the ultimate goal of this approach. So its assessment is, of course, very, very important. It's quite challenging. So you can try to break down a trustworthiness into different attributes and then try to somehow measure or score these attributes. But it's quite challenging. And because it's about systems, complex systems, as usual, you have to take into account the whole life cycle of the system. Trustworthiness of a system under design is not the same as the trustworthiness of a system which is deployed or getting updated or getting disposed of. And of course, you also have to take into account the different stakeholders. Like the trustworthiness of a consumer from a consumer or perceived by a consumer is not the trustworthiness perceived by the programmer. And what makes all that even more difficult is that we try to have a horizontal approach, as we say in standardization, or we try to be sector independent. So it will have different use cases, different AI technologies as well. So the aim is to cover anomaly detection, natural language processing, and different technologies like data-driven AI, but not only, because we often think about that. But the idea is also to cover knowledge-based AI and any kind of hybridization. So how do we traditionally achieve trustworthiness? Trustworthiness takes its roots at different levels, like the product level, the process, and even at other levels. Like the product has to be good, the process to make the product has to be good. We look also in general at the tools and the infrastructure used to develop the product and check if it's good. The people who do it have to be good, and the way people are governed also has to be good. And certification at each of its levels, at each of these levels, helps trustworthiness, of course. At each of these levels, you can have a quality approach or a risk approach. You know that in a quality approach, you try to be generally good, and in a risk approach, you somehow try to identify what can make you bad and try to solve that. So it's two complementary philosophies with the same ultimate goal, which is trustworthiness. So that's how we achieve traditionally trustworthiness. But what it is, trustworthiness? Well, people try to standardize that. This technical specification, the 5723, offers this definition. It's the ability to meet stakeholders' expectation in a verifiable way. So that's one point of view. It directly relates trustworthiness to quality, obviously. We can see that this TS offers different kinds of attributes, examples of attributes for trustworthiness. And I like the figure on the right. It's quite old. It's from Dweck. It shows the evolution of the attention for the different attributes. And you can see that there are different phases. And one here, in this phase here, the user becomes more important. And we start to talk more about usability, maintainability. And in the last phase represented here, the general environment of the system becomes more important. We talk about sustainability, interoperability. And no need to say that we are probably now in a new phase. where AI becomes more important. Well, so all these attributes are true for any system. So what is special about AI? What attributes are more important, more challenging? So there has been different works on that, and two very interesting German works from Fraunhofer and VDE that were represented here. And I don't say that because there will be people from Fraunhofer and VDE afterwards, but it says they are truly very good. There is also a very interesting work from a group called the H-Leg. So it's a European work, also very interesting. And actually, there are also people from the H-Leg. And it's people look up to this very interesting work in general. And beyond the borders of Europe, there are also interesting works in the USA from the NIST, that you maybe know, National Institute for Standardization. And there are also some sector-specific works. We represented one here about aeronautics, but there are obviously some about the automotive industry too. So what attributes are important or challenging with AI, and can we measure them? The answer to this first question is actually no. Because from a metrological point of view, it's not a measurement with a measurement tool. It's more like often more like a scoring. And that's very important from an LNE perspective. Maybe Agnès can tell you more about that after. And not only it's, so for these scores, there are some limits still. Some notions are still not fully defined, or they may be broad or subjective or qualitative. When we prepared this presentation, we tried to find some examples, but we tried not to make anyone angry, but for example, we could mention here fairness or interpretability or scalability. Some notions have already metrics, but they can have different metrics. For more reliability, you can check that different models agree with the Fleiss kappa, or you can check that a statistical model is consistent with observations, with the goodness of fit. And that actually shows that reliability can be understood in different ways. Similarly, I think you know accuracy, and it refers to precision, recall, F-score, for example. So we have all these different metrics, scores, sometimes on notions which are not clearly defined, and they will have to be aggregated. So there is also the question of how to make them comparable. That's the four-step strategy considered in the Confiance.ai program. So at first, there is a review of the characteristics. Then these characteristics, these attributes are organized in a tree or a hierarchy. So higher level attributes are progressively refined in lower level attributes. And at the end level, at the lower level, some score associations are associated to what we can call the leaves. These scores must be made commensurable. So they must be comparable because they can be different in nature. So it's kind of like, transforming apples and oranges to be able to compare them. And then finally, there is the aggregation. And here, decision aiding method, multi-criteria decision aiding method is considered. It still raises some challenges. Of course, some attributes can be in opposition. If you improve robustness, and actually Bertrand mentioned one example like that. If you improve robustness, you may lower effectiveness, for example. Or if you improve explainability, you may, that's the example which was given, you may decrease the precision. So it's a challenging step. These represent three rough clusters for the characteristics. If you try to organize them, you remember it's step 2. So there is one cluster quite specific on the system. Does the system alone technically works? So that's the bottom cluster here. Then there is a cluster more about the collaboration. Okay, the system works alone, but can the system and humans work together? So can humans understand what the system can do? Can humans understand what the system actually does? And can humans take back control? Given that it's a sensitive topic, they have to take back control when it's necessary and without adding more risk. You know, it's a classical example. People, for example, there are military drones autonomously landing, and some pilots got afraid of that it could go wrong. They took back the control, but that's actually what led to an accident. So that's about the collaboration. And then there is one cluster more centered on humans and ethics. So are the fundamental rights of humans respected, for example? That's the first row of clustering, but you can go into the more details. This is an example with more than 100 attributes. Like the row of clusters are represented with colors, even though the distinction is often not that clear. Reality is more like a rainbow. But here in green, you can see what is more about the system itself. For example, is it effective? Is it efficient? Is it durable? Is it sustainable? It's about the system, more about the system itself. Then the orange part is more about the interactions. That's what we mentioned before. So that's what we will see also what we call human oversight. And in red is about the more is centered on the human. For example, it's about discrimination, fairness, lack of bias, etc. As usual, like always in systems engineering, you can derive requirements at the system scale into requirements at a lower scale, at the component scale, where there is the algorithm and the data which fuels the algorithm. Again, so it's like systems engineering 101, but at this scale, you have to take into account that the component is part of a larger chain of components. So if the system has to be fast, the time constraint on the AI component depends on the time behavior of the other components. If the other components are slow, the AI component has to be fast. Or if you have a system which aims at detecting and moving objects, it's not necessary to have a nanometer detection system if you can only move the object at a centimeter scale. So that's kind of the basics. And of course, the mother of all battles in AI, it's the data which fuels the component, which then leads to the system behavior. So the data is, of course, very important. So what are the attributes for data? So there is a very interesting standard for that. It's 25012, ISO 25012. But the idea is that for the data, you have some attributes which are about a specific data, and some attributes which are about the data set, the whole data set. There are also some attributes which are inherent to the data, and some which are application specific. You know that, I guess you already have some examples in mind, but the data may have to be fresh enough, for example, or at least the age of the data must be adapted to the application. If you want to try to detect some COVID mutations, some new COVID mutations, you have to have very fresh data. We also say that a data set has to be representative of the population. Also, you maybe know that it can be a bit tricky, because if you cover like a population of different types of elements, for example, of different types of animals, if you take the example of animals, you have to make sure that there is enough data for the rare animals. And that may lead to you may need to introduce a bias in favor of these rare animals. So for each of these attributes, some scores also exist here. Here are two examples of some quite old scores. And again, so you can see that they are not really AI specific here. It's about the data consistency in a warehouse and the data timeliness. And we also see that they are quite simple. It's kind of ratios. But they try to formalize a complex notion into a numerical value. And these examples show that actually these scores can be partly arbitrary, and they evolve. These scores have actually evolved since they were defined. Here is an example from Thales about the accuracy of data. This is an overview, the satellite view of a seashore, and you have to detect boats. They use a score here called the PUMS to represent the uncertainty on data. It's interesting to see, it's mentioned here that this score is application specific. You can see how to understand that. So it's defined here. So these rectangles show high certainty. The yellow boxes show medium certainty, and the red boxes show low certainty. Maybe it's interesting here to see that not only you need a score, but you need to see how it's used at a system level. Here, the ergonomy is very important. The choice of representing the raw photo next to the processed photo is very interesting. Maybe the decisions you're going to take about these red boxes, very uncertain, is not the same changes, because here you have a clear view of the original data. Your decision may have been different if you only had this processed view. So it shows that, it's always a problem to see as a whole. So what are we doing now? So we are still working on the identification of the different attributes, on their structure, and on their score to make them commensurable. Because to make them commensurable, maybe you see that it's not only about normalization. For any value of if two attributes have the same value, these attributes may have the same level of satisfaction. So it's quite challenging. It's not only a normalization. What are the perspectives? So the idea is to finally have a clear taxonomy of definition and scores, and that can be an interesting input for European standardization. So Agnès and I are working at SystemX, the European Standardization Organization, and the objective is to have some standards ready for the AI Act. So within 2 years. So that can be an interesting input for standardization. There is still the important challenge of the aggregation of the scores. Also, the methodology was identified. And the good thing is that Confiance.ai benefits from different use cases. So we can test that on the environment detection of Valeo, for example, or the welding classification of Renault, or the demand prediction of Air Liquide. So that's going to be very valuable. And it was said yesterday, I guess, the more use cases we have, the better it is. So yes, that's at the end of the presentation. We hope that it made some notions clearer, and so still some work to do. But if you have some questions, we'll be happy to answer them.
Thank you, Henri. No raised hand, not this time. I don't have questions. Ah, yeah, there's one here. I think we are broadcasting, so you need a microphone. Par ici.
Hello, thank you for this presentation. I have a question about, could you give more insight about how you plan to aggregate the different metrics? Like, do you have any plan to, make a graphical representation instead of a sum or a mean, or, Thank
Yes,
you.
absolutely. And I would be happy to invite Juliette or Agnès to give more details. But so the method where for which Thales has quite some experience is called multi-criteria aided decision. And here are some more details.
Yes, multi-criteria decision making will aggregate the criteria, but we have to be sure that all criteria are commensurable, meaning that in the same scales and with some mathematical properties. Then for some of the criteria and some aggregation, we can use weighting sub, but we have to be sure that all the criteria are independent, unless we are not sound. We can use all other type of aggregator, such as max, mean, and so on, with respect to the way that the end user will perceive the trust, because this kind of approach capture the preference of the decision maker. So it's a tool that we use a lot for decision making under uncertainty or under risk, and we will apply this kind of methods in the how to assess or how to evaluate trustworthiness, using also some qualitative and quantitative metrics or way to assess it.